Welcome to Algebra 2 on our section of graphing functions. This is our last section of this chapter, which is about optimizing with linear programming. Optimizing with linear programming is a way how us to find what the maximum value is of a certain system of equations. So what we're going to do is we are going to start off by graphing the system of equations that we're given. We are going to just graph the top three equations for this example. The f of x, y we will get to at the very end. So in order for us to graph these three, we need to write them all in slope-intercept form. So the top equation, we'd have to subtract the 2x over. So we would have y is greater than or equal to negative 2x plus 3. Okay, so that's our first equation we'll graph. To get the second equation in slope-intercept form, we'd have to first add our x over. So we'd have 3y is less than or equal to x plus 9. Then we could divide everything by 3 to get the y alone. So y is less than or equal to 1/3 x plus 3. So there's our second equation. And the third equation, we'd have to subtract the 2x over. So our third equation would be y is less than or equal to negative 2x plus 10. So we take these three equations that we just put in slope-intercept form and we graph them. So top one, y is less than or equal or greater than or equal to negative 2x plus 3. We intercept at 3 and we have a slope of negative 2. So down 2 over 1, and we are going to extend that across the entire graph. Greater than or equal to, so this is included, so that's a solid line through all those using your straight edge to graph it. You can also, if you would like to mark here where this would be shaded, you certainly can. So this is y is greater than or equal to, so we're going to be on that side of the line. Second equation, y is less than or equal to 1/3 x plus 3, so our y-intercept is at 3. Slope of 1/3, so up 1 over 3. And we are going to take that across our entire graph. Less than or equal to, so this is a solid line. And if y is less than or equal to this, here we cross the y. That means we are shaded on this side of that line. Notice right now that overlap would be this section of those two lines. Okay, so this is currently the overlap region right over here. So now let's graph our third equation, which is y equals negative 2x plus 10. We have a y-intercept of 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're going to have to visualize this up here. We go down 2 over 1, down 2 over 1. Counting that very carefully, you should be able to figure out where we end up hitting the graph at. And we keep going down 2 over 1 across this entire graph, and we connect those. Now y is less than or equal to that, so we see that we should be shaded beneath this line. And if we look at where our overlap area already is, that means that this section would be where all three of those areas overlap. Okay? This is an example of what is called an unbounded region. This is unbounded because down here at the bottom there is not a definite ending point. This continues on and on forever. So what we're going to do now is we want to find the maximum and the minimum value of this depending on our function. So our function here has points x, y. These are going to be where all our vertices are. Our vertices are where our lines intersect. So in this case, we just have two of them. This one is at the point 0, 3, and our other one is at the point 1, 2, 3, 1, 2, 3, 4, 3, 4. So we're going to plug these points into this equation. So f of xy is equal to 5x plus 4y. So f of 0, 3, so 0 we plug in for x, 3 we plug in for y, would be 0 plus 4 times 3, which is 12. And we also plug in our 3, 4, which would be 5 times 3 plus 4 times 4, or 15 plus 16, which is 31. Okay. Now here we have two values. We got 12 and we got 31. Because this is unbounded, we also want to try some other value in this shaded region. It doesn't really matter which value you pick, but you do want to try to choose one that's a ways away. So here we will choose this value right here. That is at the point 1, 2, 3, 4, 5, and down 1, 2, 3, 4, 5. So I'm going to plug in the point 5, negative 5. And when I plug this point in, I would have 5 times 5 plus 4 times negative 5, which gives me 25 minus 20, which is 5. Now compare 5 to 31 and 12. Notice that 5 is less than both of those. So since that's less than both of those, that tells us that we have no minimum. There's no minimum value here. And there is a maximum, and the maximum here that we got was 31, because 31 is the biggest number, and it happened at our vertex 3, 4. So what this means is that this is just a pretend function that I made, but there are functions like this that represent various things out in the real world. If we were looking to figure out where we could make the maximum amount of profit here, the maximum amount of profit would be 31, and at the point 3, 4. So we would want to order 3 of something and 4 of something else, whatever they would happen to be representing. Okay, so now we're going to do another one. Our second set of equations here. So we're going to go ahead and graph. So the first one is x is greater than or equal to 1. Well, if x is 1, then it only has an x-intercept, no y-intercept, so it is a vertical line at 1. And greater than or equal to, we will be over to the right of that. Y is greater than or equal to 0. So that would be a horizontal line at 0. And if we are greater than or equal to 0, that would be above it. So currently, this area over here would be the overlap that we have for our shaded region. Our third equation, we need to get this in slope-intercept, so we're going to subtract the 2y over. So we have y is less than or equal to negative 2x plus 6. I'm sorry, I meant to say subtract the 2x over to get y alone. Graphing that line, we have a y-intercept of 6, 1, 2, 3, 4, 5, 6, and a slope of negative 2. So down 2 over 1, down 2 over 1, and so on and so forth across our whole graph. We will connect that together with the straight edge. And now we are less than or equal to it. So if we're less than or equal to it, that's the values underneath here, which would mean we have this small triangle is our shaded area. Okay. So now we have the shaded area. We've figured out where these overlap. And that would be our function graphed. So now we want to pick out where our vertices are. So here are our 3 vertices. They happen, this point is at 1, 0. Our next point is at 1, 2, 3, 0. And our third point is at 1, 1, 2, 3, 4, is at 1, 4. All right, so we are going to figure out what our function is for each of these. Now notice here on this graph that this is a bounded region. This is bounded because the graph is clearly confined to this area. Okay, so now we just plug in the values that we got for our vertices. So at 1, 0, that means x is 1 and y is 0. So 3 times 1 plus 0 is 3. F of 3, 0, so our x is 3, our y is 0. 3 times 3 plus 0 is 9. And f of 1, 4, our x is 3 and our y is 4. 3 times 1 is 3 plus 4 is 7. So now to find the maximum and the minimum, we look and we go, okay, 9, that is clearly a maximum, and 3 is clearly a minimum. So we would say we have a minimum of 3, and it happened at the point 1, 0. And here we have a maximum a maximum of 9, and it happened at the point 3, 0. Okay, so the graph and the min and the max would be your complete answer. What this would represent in a real-world situation is perhaps we have two things that we have to be greater than here, and then there's only a certain amount of manpower, a certain amount of people that can work, and this line could represent that. And so the shaded area could be your productivity of creating something. And your productivity for what you get for profit, in this case, would be best at that 3, 0 point. So that's how much you would order of each one. Okay, so that's optimizing with linear programming.